All right, thanks. So I'm just wanted to thank the organizers for having me here. I'm very excited to be at this workshop. So this last summer, I had the opportunity to go to Oak Ridge National Laboratories and work with Max Gunsberger and Pablo Celestin. And so this is kind of a summary of some of the work that I started there. So we wanted to look at linearized peridynamic models, and we noticed that there's not so many generalizations to higher antisymmetric behavior. So we wanted to try and create some models for more anisotropic type models. Okay. Yeah. All right, so first an outline, I'm going to give a little background information. We're going to talk a little bit about classical linear elasticity. I'll give a very brief introduction of peridynamics since this is the fourth presentation on it. And then we're going to talk about our derivation for this elastic and isotropic model that we created. We're going to have a bond-based one, and then we also have a state-based version as well. Okay. And then I'll just finish up with some future work and some conclusions. All right, so first, classical linear elasticity. In the classical setting, you have your stress and strain tensors related via this generalized Hooke's law. This equation here, and so you have this fourth order tensor C called the elasticity tensor. And it has the following symmetries as minor symmetries, so you can, it's invariant changing the first two indices or the last two indices. And those are just inherited from the stress and strain tensors. You also have the major symmetries, which is where it's invariant interchanging the first two sets of indices with the last two sets of indices. And that just comes from relating the strain energy density to it, to the CIJKL, your elasticity tensor. You'll get a second order or derivative, and then you can just change the order differentiation. So if you have C, it originally has 81 constants, but with the symmetries, it reduces down to 21 independent terms. And your classical equation of motion, Newton's second law, is given by this right here. You've seen it several times in previous presentations today, where U is the displacement. All right, so linear elasticity, there's only 8 symmetry classes that you can consider. This has been proven several times. There's one very nice paper on it by Chadwick, Vianello, and Cohen. And they go through this and show that there's exactly 8 symmetry classes for linear elasticity. So you have triclinic, which is your most general one. You have no planes of symmetry. Monoclinic, you have reflections across a plane. Orthotropic, you have three orthogonal planes of reflection. Transversely isotropic, you have a plane of isometry, meaning it's direction independent in that plane. And then you have reflections across that plane. A couple others, cubic, you have all these symmetries of a cube. And then isotropic, which is what you see for most peridynamic models, that's where you have direction independence. So Pablo's model was isotropic. All right, so peridynamics, again, our goal is kind of be able to model damage usually. That's kind of the benefit of it. It has some other benefits. You can create communication across length scales, model complex fracture patterns. This again was invented by Stuart Silling back in 2000 in his famous paper now. All right, so yeah, fundamentals. Yeah, I'll do it one more time. I mean, we've seen it 3 times, but I'll do one more. So fundamentals of bond-based non-local theory. So we assume in the reference configuration there's this kind of connection initially between points. And as you deform these points that were originally connected, they can interact with each other over deformation distances. So they interact through these things that are sometimes called bonds. Your equation of motion, this is the peridynamic one. It's similar to the classical one, except you have, oops. Oh, there we go, sorry. Except you have this term here, which is just your internal forces. This is your bond forces from all of your internal ones. Okay, so this would be the forces on X from all of its surrounding points. So how is damage modeled? Well, we assume some criterion. Usually it's based on how far the bond stretches. If it stretches past a certain length, it'll break irreversibly. Broken bonds carry no force. That kind of transfers the load to other bonds, and you can have progressive failure from there. And so for instance, when we're modeling damage, Pablo gave some examples of that. But you'll have damages at nodes, and you can kind of follow a crack path based on the damage at each of the nodes. All right, so let's talk about our anisotropic model. We had several goals in mind when we were trying to create it. One, we wanted to be described by the classical elasticity tensor. And this is mainly for implementation purposes. The classical elasticity tensor, these constants have been measured for a lot of different materials. We don't have to measure new things. We wanted the model to be able to describe any of the 8 symmetry classes of linear elasticity. And then thirdly, we wanted to imposing material symmetries on the elasticity tensor since our peridynamic model is described with the elasticity tensor. If we impose those symmetries on the elasticity tensor, we want those same symmetries to be absorbed into the peridynamic model. So I don't want a monoclinic elasticity tensor giving me a peridynamic model that has, for instance, just cubic symmetry or triclinic symmetry. And then lastly, we want the corresponding peridynamic model to have the correct degrees of freedom. Okay, so in the general case, the triclinic model, there's 21 degrees of freedom. We want the peridynamic one to also have 21 degrees of freedom. All right, so this is the bond-based linearized peridynamic equation of motion here. And so what we're going to do is we're going to perform a Taylor expansion on this term here. And we make a further assumption for physical reasons that lambda of c is equal to lambda negative c. We apply a Taylor expansion on this term right here. And your odd order terms all drop out. Your 0 order term cancels with this one. And so what you're left with is just 2nd order, 4th order, 6th order. We drop off the higher order terms just like you do in the classical case. And what we're left with is this one. And so if you remember back to the classical one, you had the same equation except instead of this term here, you had the classical elasticity tensor,Cijkl. And so what we do to make a relation between the models is we just set this equal toCijkl. So this is our formulation for the bond-based model. And so from the modeling perspective, all we have to do is we have to determine what this lambda should be, called the micromodulus function. Oops. All right, so there's some limitations from the bond-based theory, and that's why this model can't do everything that we had in mind for our requirements here. It's not going to have the correct number of degrees of freedom in particular. So this is just an example of this. In classical elasticity, for an isotropic case, you have exactly 2 constants, or 2 degrees of freedom. For the bond-based one, you only have 1. So if we assume that our micromodulus function's isotropic, meaning it's direction independent, we can solve this equation here. You can prove this by considering a spherical expansion here. Expand it out to this, and you find these relations here. And this is actually a well-known result. Stuart Cillian actually mentioned this in his first paper, that the effective Poisson ratio is just going to be a 4 for 3D. And so you can do this for the other types of symmetries. So isotropic, you only end up with 1, whereas you have 2 in the classical case. Cubic, you end up with 2, but you're supposed to have 3. Transversely isotropic, you have 3, but you're supposed to have 5. Triclinic, you have 15, but you're supposed to have 21. Okay. And the others are there as well. I summarized it here. So these are the bond-based limitations here. This is the maximum number of degrees of freedom you can get in each of these cases. Okay. This actually has some nice connections to the classical theory, which I will talk about a little bit later here. And these are the classical elasticity or state-based peridynamics as well. Okay, so one proposition we proved, we showed that if we impose symmetry on our micromodulus function, then the corresponding elasticity tensor will also have that symmetry. So if we just assume this relation here, we impose a symmetry on lambda, then the corresponding elasticity tensor will also have the exact same symmetry. Unfortunately, converse isn't true, as you might expect, because this is inside an integral. I impose a symmetry onCijkl. It's not going to impose a symmetry on lambda necessarily. But if we pick lambda appropriately, it'll be an if and only if. It'll be equivalent. All right, so this has been kind of the common method of introducing anisotropy into the bond-based models. This has been done in a few papers that I've seen. They will basically take this micromodulus function and they'll assume a spherical expansion of it in this form here, where PM are again the associated Legendre functions. And it turns out if you do this expansion past the fourth order, you don't get any more generality in C. So you can keep expanding out to higher orders, but you're not going to get any more generality in C. So if you expand out to fourth order, for the triclinic case, you'll get 15 constants. You can expand out further, it might be a modeling choice, but you're not going to get any more generality in C. Okay. So here's two examples. The first one, Pablo mentioned these guys in his talk, Gahari, Iannucci, and Curtis. They were trying to do a transversely isotropic model. So they basically took a spherical expansion and they killed off terms that didn't have that weren't symmetric with respect to transverse isotropy. And they came up with this model here. They expanded out to the eighth order. In 2, so Izad, Han, and Libanu, they looked at an orthotropic model. They did just a fourth order expansion. They get exactly the right number of constants. It worked out very well for them. This is the maximum number you can get. And you can just cancel off the ones that don't have orthotropic symmetry. Some of the other symmetries were a little more difficult, actually, and that might be why you don't see them as much in literature. For instance, cubic was a little bit problematic because if you just kill off the terms that have the incorrect symmetry, you end up with just one constant, even though you should be able to get 2. And that's because actually 2 of the constants come together to form a new function. So you have 2 terms. For instance, these 2 would come together to form a new function that's transversely isotropic, or cubic, rather. All right, so I'm going to talk a little bit about this model here because we made some simulations based on this model in the hopes of being able to adapt it to other types of materials later. So in addition to that micromodulus function, they also wanted to have an anisotropic bond breaking condition. So they assumed that this critical stretch has 0. They did a spherical expansion on it as well in the same form that they did for the micromodulus function. And then to compare it to physical constants, Silling and Ascari, they originally related the bond breaking criterion to the critical strain energy release rates via this formulation here. What Gahari, Iannucci, and Curtis did is they looked at 2 different critical strain energy release rates. So they just did it on 2 different planes. So let's be anisotropic. Okay, so this is just application I wanted to go over. This is first Gahari, Iannucci, and Curtis did this first, and then I reproduced it while I was at Oak Ridge. Wow, the graphic's not going to look very good, I think, actually. All right, so what they wanted to do is they wanted to reproduce this famous medical experiment. So they took this cortical bone in this medical experiment, and they took 2 pins into it and pre-notched and pulled it apart. They noticed that the bone was anisotropic and that the crack tended to follow the main axis of the bone, no matter how they originally marked this original pre-notch. So you can do this with this simulation here. So we oriented the main axis of the bone at some angle with the horizontal. I think in this simulation it's going to be at 1 radians from the horizontal. And you'll notice that the crack, in an isotropic case, would crack straight across if you were to pull these 2 pins apart, but in this case it's actually going to go up to the left at about an angle of, well, 1 radians. Okay. So let me try running this. We'll see how it looks. So this is a video of the strain energy. And so these 2 pins are pulling apart and the strain energy is going to grow, and eventually it's going to get too much and our bonds are going to start breaking and they'll go off in this direction for the crack. Now I'll kind of speed this up a little bit because it's going to take a while to rise. So you see here we get a crack starting to form, and it looks a lot better on my computer. The graphics aren't coming out very well, unfortunately. But the crack slowly starts growing off in this direction here at an angle of about 1 radians with the horizontal. Yeah. Okay. So in addition to showing that it cracks in this direction, they also, so that it matches well with experimental results for the maximum load that the bone could support as well. It was off by like 5% or so from the experimental results that they found of around 98 newtons for the maximum load that this bone could sustain. And so this was first measured by these guys for cortical bone. All right, so another application they did was these polycrystalline simulations. And so in the simulation, they took a polycrystalline formation of alumina, which is used in ceramics, for example, and they prescribed boundary conditions where this plate is pulled apart from the top and the bottom. And they wanted to see how the fracture would appear throughout this plate. And so they assumed each of these grains was transversely isotropic for alumina, and they gave it a random orientation for the plane of isometry within each of these. So they randomly oriented the plane of isometry in each of these individual grains here, and they defined the peridynamic function on each of these grains based on that anisotropy in each of the grains. Okay. They also had to define the bond function between the grains, and for that they just took the average of the two. And then lastly, they used the fracture energy to get the bond breaking criterion. They only had one constant, because it's probably not measured for the individual grain, I would imagine, but they had just one constant for alumina. And so what they did is they had it defined for the interior of the grain, and then for the boundary bonds, they had to basically assume a ratio based on that one. So they would either assume it's weaker or the same. So I have two simulations here. We'll see how it looks here. So in the first one, they assumed that this fracture energy was the same. And it's going to be near the end here. Yeah. So this is where they assume it's the same. And in this case, the fracture is not going to really distinguish between grain boundaries and grain interior. It's just going to go straight across that. And in this case here, this is where the grain boundary is basically half the strength of the grain interior. And so you can actually see some of the grains that are over there. They're forming here. It goes around the grains rather than through them. Okay. Maybe it's not obvious from that picture, but yeah. So you see some of the grains over here are actually, it goes around them instead of through them. Okay. So this was our first bond-based model. So we also tried a spherical expansion first, and it took us quite a while to figure out how the formulation should be. The main problem was when we plugged in the elasticity constants, we wanted to have it reduced to the correct symmetry, and that's where a lot of the trouble arose. So this is a fourth order expansion, but some of the terms are missing. You'll notice the first order terms, so P1, 0, P1, 1, they're gone, as well as P3, 0, all of the P3 ones are gone. Okay. So after mostly a lot of trial and error, we came up with this model. And I think for fourth order expansions, this is probably the only one that actually works. And we'll see kind of a better representation of this a little bit later. But with this formulation here, you can solve for the constants A0, 0, A2, 0, and so on in terms ofCijkl. If I plug in a certain symmetry intoCijkl, this lambda will also share that exact same symmetry. Okay. And it'll have the correct number of degrees of freedom for the bond-based case anyways. So for triclinic, you'd get 15, 9, 6. It's the maximum number you can get, and it will have all the right symmetries when you reduce it. All right, so we found a better way to kind of formulate this model. It actually ends up being the exact same model, but there's an interesting relation between these. I haven't studied engineering, so I didn't see this, but Pablo figured this out. If you look at these here, there's actually a well-known theory in linear elasticity that actually has this exact same formulation here. And that's called the Cauchy relations. If you impose the Cauchy relations, these are the exact number of independent constants you will get. Okay. So back in the 1830s, Navier, Poisson, Cauchy, and others, they developed molecular models of elastic bodies. They prescribed certain properties on this, and then building up to the macroscopic scale, this led to these 6 relations. So at the time, this was somewhat controversial whether the 21 case or this 15 case was correct. The 21 case won out for the most general case, but I mean, there's still some applications of this. And it turns out that bond-based peridynamics is equivalent to when the Cauchy relations hold. And so these are kind of when the Cauchy relations hold, you have central forces, for instance, and a few other characteristics here. So with that information in mind, and then we looked at one other interesting paper here, this Heel and Eitan. They did a lot of algebraic studies of the elasticity tensor, and they noticed that the elasticity tensor could be decomposed into two irreducible tensors, one of which was one of which is symmetric, and one which is dependent only on terms in the Cauchy relations. And in fact, when the Cauchy relations held, that second tensor is 0. So we thought, well, wait, maybe if we assume that the bond-based portion of the model is given by a completely symmetric tensor, it'll work. And it ends up, that works quite well. This is actually equivalent to that spherical expansion we did before. It's identical. You can show when you solve for it, this is exactly the same model to get. This one's a lot easier to remember and a lot simpler looking. It also gives you some intuition on how to choose the state-based portion of your micromodulus function. So when you solve this, this is the relation between your peridynamic constants and your elasticity constants. So this is with the Cauchy relations imposed. And it has some interesting structure. We haven't studied this too much yet, but for instance, these 6 terms here correspond to, they're 0 if you go down to the monoclinic case, and the exact same indices over here would be 0 if you went down to the monoclinic case. Similarly, orthotropic case, you drop these 3, you drop these 3 over here for the orthotropic case. So there's some interesting block nature here, but we haven't really looked into this too far yet. But this is the relation. It's a nice kind of comparison between the two. And then later, we found this paper by Azad, Han, and Libanu, and they had this orthotropic model they did by spherical expansions. This is exactly the same model you would get if you used ours. This is for orthotropic, though. Ours is more general. It does triclinic or any of the others. All right. And so this was one of the ones that was a little bit harder for me. Before was the cubic model, and that's because some of the terms compared, but with this new formulations, it's quite simple. You just plug it in and you're done. It's a piece of cake. So you just take your lambda defined like this, I lost, okay. You take this lambda defined like this, you solve for the elasticity constants in terms of your you solve for your peridynamic elasticity constants, if you want to call them that, in terms of your classical elasticity constants. And then you can plug in cubic symmetry, and you'll end up with exactly this model. Okay. You can also do bond breaking criteria in a similar manner, just like Gahari, Iannucci, and Curtis did. You could choose one of this form, and then you can just do it across different planes. This one's a little bit problematic because I don't know if we would have all the physical constants necessary to do this. For instance, in the triclinic case, you would need fractionaries across 15 different planes, which I'm not an engineer. I don't know if they measure that, but I don't know if anyone has that recorded. All right. So now we want to generalize a little bit to the state-based peridynamics. So it's a generalization of the bond-based peridynamics. And the generalization is it allows materials to material responses to depend collectively on the deformation of all bonds connected to that point. And so this allows us to have dependence on collective quantities such as volume change and shear angle. And what this will also do is allow us to remove the constraints on the elasticity tensor, because remember our original goal was to have 21 independent constants. So we need to have a more general model. And I should mention state-based peridynamics was first introduced by these guys here, this famous paper back in 2007. All right, so we had a very nice introduction to the state-based model and a derivation of it. This is the linearized formulation of it here. And so this looks very much just like the bond-based term we had here. We have this other term here, this dilatation term here. This is where the state-based modeling comes in. We basically need to pick how this micromodulus function should be chosen. Okay. And so like before, if you do a Taylor expansion, drop higher order terms, you'll end up with this equation here. And so again, we just relate this to CIJKL, just like we did for the bond-based case, and you have this relation here. So this again is exactly like we had in the bond-based case. We just pick up this extra term for the state-based one. Okay. And if you have this holding, you impose symmetries on kappa and lambda. Those same symmetries will be inherited by CIJKL. The converse isn't true without restrictions, of course, on kappa and lambda. And so what we do for the state-based term is we take these two formulations here. So this is kappa, and this is lambda, so S is going to be a completely symmetric one. Kappa, we impose some symmetries on kappa, or alpha rather, or A, I should say. Impose some symmetries on A, we have the minor symmetries imposed on A. But the formulation of A is not unique, unfortunately, so we looked at all possible formulations of A such that when we reduce the model down, you would get the correct symmetry and the correct degrees of freedom, but it's not unique. And so that's kind of where we are with this model. We have one that works. We picked one that was kind of aesthetically appealing, but whether one formulation of A is better than another, we don't know yet. One possible way of figuring out how it should be is possibly thinking of this peridynamic formulation. You had these guys. Oops, I guess I don't have that. Let me go back. Yeah, Heel and Eitan. So what they looked at is they looked at this, the classical elasticity tensor. They decomposed it into two irreducible pieces. This was on the general linear group. Composed into a completely symmetric one and then to a different one that was completely dependent on the Cauchy relations. Now we think that possibly the state-based model could also be decomposed like this. Perhaps if we imagine a generalized peridynamic model, we could have a state-based tensor and a state-based tensor and a bond-based tensor. And so that's how we have it formulated here. But they also did some other research on the decompositions of that peridynamic tensor, or sorry, on the classical elasticity tensor. It could be further decomposed if you consider groups of rotations. And we think if we impose those same formulations for this breakdown here, this might result in just one single model. But we're not quite sure yet. That's some research I'm planning on doing, hopefully while I'm here. So some future work, we're going to develop an anisotropic bond breaking criterion for the state-based model. We want to compare various formulations of the state-based portion of the model, since we have several different possibilities. We want to numerically implement our state-based model. That's something I'll probably get done while I'm here. And then we want to consider anisotropic models of other types of material responses, such as plasticity. So you could assume elastic, and then you have a plastic response after that. So you'd use our model for the plastic response, and then for the elastic response, and then after that you have some kind of plastic response. All right, so just a conclusion. We've created a bond-based and state-based linearized elastic model with following properties. The model is defined by commonly measured material quantities, such as the elasticity tensor. We can model any of the 8 symmetry classes of linear elasticity. The symmetry in the elasticity tensor is equivalent to symmetry within the micromodulus function. So if you have symmetry in one, you have symmetry in the other. And the peridynamic model has the exact number of degrees of freedom as the classical elastic model for each symmetry. And here's some references. Anyways, thank you for listening to my talk.